Imagine traveling from Los Angeles to San Francisco in just 30 minutes without airports, boarding delays, turbulence, or traffic congestion. You step into a sleek capsule, the door seals, and within seconds, you're accelerating smoothly through a dedicated tunnel at speeds rivaling commercial aircraft right on the ground. It sounds like pure science fiction, but here's the reality: Hyperloop is not limited by imagination, it is limited by engineering. And at the center of this revolutionary system lies civil engineering. What does it truly take to design hundreds of kilometers of near-vacuum tunnels, capable of maintaining structural integrity under continuous pressure differentials? How do engineers ensure millimeter-level alignment for a levitating pod traveling at more than 1,000 kilometers per hour? And how can infrastructure remain stable against thermal expansion, seismic activity, long-term settlement, and material fatigue? Today on Civil Engineering Edge, we dive deep into the extraordinary infrastructure challenges behind Hyperloop. We'll explore how tunnels, tracks, foundations, and materials must be re-engineered from first principles to support one of the fastest transportation systems ever envisioned. This is not just a transportation story, it's a civil engineering revolution. Throughout history, every major leap in transportation has been driven by bold engineering ideas. Roads connected civilizations, railways transformed economies, highways reshaped cities, and aviation shrank the world. Yet each system eventually encountered physical and economic limits. Hyperloop represents a radical departure from incremental improvement. Instead of pushing existing systems slightly faster, it proposes an entirely new operating environment to control near-vacuum infrastructure designed for ultra-high-speed ground travel. For civil engineers, this is a defining challenge of our generation. Hyperloop infrastructure demands unprecedented precision, structural stability, and durability over massive distances. Tunnels are no longer passive structures resisting soil loads. They become active systems responsible for maintaining pressure, alignment, and safety at extreme speeds. In this video, Civil Engineering Edge explores how civil engineering principles are being reimagined to make Hyperloop possible and why its infrastructure could redefine how we design transportation networks for the future. The impossible dream. Reimagining transportation for decades, transportation engineering followed a predictable path: incremental improvements built upon existing systems. Trains became faster, highways wider, and aircraft more fuel efficient. However, each advancement faced unavoidable physical constraints: rolling friction, aerodynamic drag, noise, energy loss, and land availability. Hyperloop challenges this entire evolutionary model. Instead of fighting friction and air resistance, Hyperloop removes them almost entirely by operating in a near-vacuum environment with magnetically levitated vehicles. From a civil engineering perspective, this shifts the challenge away from propulsion and toward infrastructure perfection. This is why Hyperloop was long considered an impossible dream. It demands infrastructure tolerances far tighter than conventional rail or metro systems, continuous structural performance across hundreds of kilometers, minimal curvature, and near-perfect alignment, absolute control over settlement, vibration, and deformation. Traditional infrastructure is designed with allowances, minor misalignments, localized settlement, and flexible tolerances. Hyperloop allows none of these luxuries. At ultra-high speeds, even millimeter-scale deviations can result in unsafe dynamic responses. Reimagining transportation through Hyperloop means transforming infrastructure into a precision-engineered system, more comparable to aerospace structures than conventional civil works. Tunnels behave like pressure vessels, guideways act as alignment-critical instruments, and foundations must maintain geometric stability for decades. The impossible dream becomes achievable only when civil engineering evolves beyond traditional design philosophies and embraces extreme precision, long-term monitoring, and system-wide integration. Introduction to Hyperloop. What does ultra-high speed really mean? Hyperloop is often loosely compared to high-speed rail, but this comparison dramatically understates the engineering leap involved. High-speed rail systems typically operate between 250 and 350 kilometers per hour, approaching the physical limits of wheel-rail interaction and aerodynamic efficiency. Hyperloop aims to exceed 1,000 kilometers per hour, nearly 3 times faster, while remaining a ground-based system. At such speeds, infrastructure behavior changes fundamentally. Dynamic forces increase non-linearly, vibrations become critical, and structural imperfections are amplified. For civil engineers, ultra-high-speed travel demands absolute control over geometry, stiffness, and continuity. Unlike conventional rail tracks, which tolerate small deviations corrected through maintenance, Hyperloop guideways must maintain alignment continuously and autonomously. Even slight curvature irregularities can induce unacceptable lateral accelerations at extreme speeds. Travel times become transformative. Intercity journeys measured in minutes rather than hours. Regional connectivity without airports, economic integration across megacities, but these benefits come with immense infrastructure challenges. Extremely large curve radii, rigid control of vertical and horizontal alignment, suppression of vibration, and resonance passenger comfort governed by acceleration limits. Ultra-high speed does not merely describe velocity, it defines an entirely new infrastructure performance standard. Civil engineering shifts from building durable structures to building precision systems capable of sustaining speed safely and reliably. Why now? The convergence of technology. The idea of Hyperloop is not new, but the ability to construct it is. What makes Hyperloop feasible today is the convergence of several mature technologies, each deeply influencing civil infrastructure design. First, magnetic levitation systems have advanced to a level of reliability and controllability suitable for commercial applications. These systems demand guideways with extremely tight tolerances, transferring unprecedented responsibility to civil engineering design. Second, large-scale vacuum technology has matured through industrial and scientific applications. Modern pumping systems, airtight seals, and real-time pressure monitoring enable long-distance, low-pressure tunnels to be realistically maintained. Third, advanced construction materials now allow engineers to design infrastructure that is lighter, stronger, and more durable. Ultra-high-performance concrete, composite reinforcements, and corrosion-resistant alloys significantly reduce deformation and long-term maintenance demands. Fourth, digital engineering tools including BIM, digital twins, AI-based alignment optimization, and sensor-embedded structures allow continuous monitoring and predictive maintenance of Hyperloop infrastructure. Together, these technologies transform Hyperloop from a visionary concept into a constructible engineering system. Civil engineering is no longer adapting to transportation, it is leading its evolution. The core problem, friction and air resistance. Every transportation system loses energy to friction and air resistance. At high speeds, aerodynamic drag becomes the dominant force, increasing exponentially and making further speed gains economically and physically impractical. Hyperloop eliminates this limitation by radically altering the operating environment. By reducing air pressure inside tunnels to near vacuum levels, air resistance is reduced to a fraction of that experienced by conventional trains or aircraft. Simultaneously, magnetic levitation removes mechanical friction entirely. However, these advantages place extraordinary demands on infrastructure. Hyperloop tunnels must maintain vacuum integrity over vast distances while resisting soil pressure, seismic forces, and thermal expansion. Unlike conventional tunnels, which primarily resist external loads, Hyperloop tunnels must also manage internal pressure differentials, effectively functioning as long, continuous pressure vessels. For civil engineers, the challenges include Airtight joint design, long-term material durability, settlement control, structural deformation limits measured in millimeters. Any failure in infrastructure directly compromises speed, efficiency, and safety. Hyperloop succeeds only when civil engineering creates an environment where friction and air resistance are nearly eliminated, making infrastructure the silent enabler of ultra-high-speed travel. The unseen battlefield, battling the vacuum. At the heart of the Hyperloop concept lies an invisible yet relentless adversary: air pressure. While passengers experience smooth, silent motion, the infrastructure is engaged in a continuous battle to maintain one of the most challenging environments ever attempted in large-scale civil engineering, a near vacuum extending for hundreds of kilometers. Unlike laboratory vacuum chambers or industrial pipelines, Hyperloop tubes are megascale civil structures exposed to soil loads, temperature variations, seismic forces, material aging, and long-term settlement. Every joint, seal, and material interface becomes a potential point of failure. For civil engineers, the challenge is not simply creating a vacuum, it is preserving it continuously, safely, and economically over decades of operation. A pressure loss of even a few percentage points can drastically increase aerodynamic drag, energy consumption, and system instability at ultra-high speeds. This unseen battlefield transforms traditional tunnel design philosophy. Instead of merely resisting external loads, Hyperloop tunnels must maintain internal environmental integrity under dynamic structural behavior. Thermal expansion alone can cause millimeter-level changes in geometry, threatening airtight seals across long distances. Furthermore, maintenance strategies must operate without frequent system shutdowns, demanding redundant pumping systems, compartmentalized tunnel sections, and real-time pressure monitoring integrated into the structure itself. In Hyperloop infrastructure, vacuum maintenance is not a mechanical afterthought, it is a core civil engineering responsibility. The success of the entire transportation system depends on the tunnel's ability to fight this invisible battle continuously, silently, and flawlessly. Engineering the near vacuum, maintaining IT across hundreds of miles. Creating a near vacuum over hundreds of miles is unprecedented in civil infrastructure. Unlike short vacuum pipelines, Hyperloop tunnels stretch across varied terrain, geological conditions, and climates, each introducing unique engineering challenges. The first strategy is segmentation. Hyperloop tunnels are divided into manageable sections, each isolated by high-performance bulkheads and pressure control valves. This allows localized pressure management and prevents total system failure in the event of a leak. Next comes distributed vacuum pumping. Instead of relying on centralized pumping stations, Hyperloop infrastructure uses a network of pumps placed at regular intervals. This reduces pressure gradients, improves efficiency, and allows rapid response to localized leaks. From a civil engineering standpoint, joint design is critical. Expansion joints must accommodate thermal movement while maintaining airtight seals. Traditional tunnel linings are insufficient. Hyperloop requires multi-layer composite linings incorporating structural layers, sealing membranes, and protective coatings. Material selection plays a decisive role. Concrete mixes must exhibit extremely low permeability, minimal microcracking, and long-term dimensional stability. Steel and composite liners must resist corrosion, fatigue, and creep over decades. Real-time monitoring is embedded into the structure itself. Sensors continuously track pressure, temperature, deformation, and leakage, feeding data into digital twins that predict maintenance needs before failures occur. Maintaining a near vacuum across hundreds of miles is not achieved through brute force, it is achieved through system-level engineering, where civil, mechanical, and digital systems operate as one integrated infrastructure organism. Structural integrity under immense pressure differentials. Hyperloop tunnels face a unique structural challenge: continuous pressure differentials acting across their walls. Unlike conventional tunnels, which mainly resist external soil and groundwater pressures, Hyperloop tubes must also withstand the inward force created by internal low pressure. This pressure differential generates significant hoop stresses in tunnel linings, effectively treating the structure as a long, buried pressure vessel. Even small deviations in circularity or material uniformity can lead to stress concentrations and long-term fatigue. Civil engineers must design tunnel linings with exceptional geometric precision, high compressive strength, and crack control. Microcracks often acceptable in conventional tunnels become unacceptable in Hyperloop infrastructure due to leakage risks. Sealing systems face extreme demands. Gaskets, membranes, and joint seals must maintain airtightness while accommodating thermal expansion and contraction differential settlement, seismic movement, long-term material aging. Foundation behavior becomes critical. Uneven settlement introduces bending stresses into tunnel segments, increasing the risk of seal failure. As a result, Hyperloop corridors require ground improvement, deep foundations, or elevated pylons in weak soil regions. Seismic design adds another layer of complexity. Structures must flex without compromising vacuum integrity, demanding innovative joint and liner designs capable of controlled deformation. Ultimately, structural integrity in Hyperloop tunnels is not about strength alone, it is about precision, durability, and resilience under continuous pressure differentials never before demanded of civil infrastructure. The airlock problem, entering and exiting the vacuum. One of the most complex operational challenges in Hyperloop infrastructure is the airlock system, the interface between atmospheric pressure and the near-vacuum environment of the main tube. Unlike spacecraft airlocks used infrequently, Hyperloop airlocks must operate continuously, rapidly, and reliably for commercial passenger throughput. Each cycle involves controlled pressurization and depressurization without disrupting the vacuum integrity of the main system. From a civil engineering perspective, airlocks are structurally and operationally critical nodes. They experience repeated pressure cycling, generating fatigue stresses in walls, doors, and seals. Materials must resist deformation while maintaining airtightness over thousands of cycles per day. Airlock chambers are designed as reinforced pressure structures, often incorporating circular or spherical geometry to minimize stress concentrations. High-performance sealing systems ensure minimal leakage during operation. Energy efficiency is another major concern. Rapid pressure changes consume energy, so engineers optimize airlock volume, cycle timing, and pressure gradients to minimize losses while maintaining safety. Redundancy is essential. Multiple airlock chambers allow continuous operation, even during maintenance or failure of individual units. Emergency protocols must safely isolate pods and tunnel sections in the event of malfunction. The airlock problem highlights a fundamental truth of Hyperloop engineering. Interfaces are often more complex than the system itself. Solving this challenge requires civil engineers to think beyond static structures and design dynamic infrastructure capable of repeated environmental transformation. Groundbreaking tunnels. Beyond today's TB-MIS, tunnel construction has always been one of civil engineering's most complex undertakings. From mountain rail tunnels to deep metro systems, engineers have steadily improved tunnel boring machines, TB-MIS, materials, and construction methodologies. However, Hyperloop infrastructure pushes tunneling beyond its current technological boundaries. Unlike conventional tunnels designed for trains or utilities, Hyperloop tunnels must meet extraordinary requirements for straightness, smoothness, airtightness, and long-term dimensional stability. A deviation acceptable in metro tunnels becomes unacceptable at ultra-high speeds. Hyperloop tunnels are not merely underground corridors, they are precision-engineered conduits for near-supersonic travel. Traditional TB-MIS are optimized for safe excavation and structural stability, not for micron-level geometric precision over hundreds of kilometers. Hyperloop demands a new generation of tunneling technology capable of maintaining continuous alignment control, minimizing segmental joints and tolerances, integrating sealing systems during excavation, reducing post-construction correction. Furthermore, Hyperloop tunnels must be constructed faster and more economically to be commercially viable. This drives the need for continuous excavation, automated lining installation, and real-time alignment correction during tunneling operations. The result is a paradigm shift in tunnel engineering. Hyperloop forces civil engineers to rethink TB-MIS not as excavation tools, but as precision manufacturing systems operating underground. This section explores how tunneling technology must evolve to meet one of the most demanding infrastructure challenges ever proposed: the new era of tunnel boring, speed, precision, and continuous excavation. Hyperloop infrastructure requires a fundamentally new approach to tunnel boring. Traditional T-beams operate in discrete cycles: excavate, stop, install lining segments, and then resume. While effective for conventional tunnels, this process introduces alignment variability and construction inefficiencies unacceptable for Hyperloop systems. The future lies in continuous excavation TB-MIS, where excavation, spoil removal, lining installation, and sealing occur simultaneously. These advanced machines function more like underground assembly lines than conventional construction equipment. Precision is the defining requirement. Hyperloop TB-MIS must incorporate laser-guided navigation systems, inertial measurement units (IMUs), AI-assisted alignment correction, real-time geometry verification. These systems allow continuous micro-adjustments to maintain near-perfect straightness. Instead of correcting errors after construction, precision is enforced during excavation itself. Speed is equally critical. To make Hyperloop economically feasible, tunneling rates must exceed those of current metro projects. Continuous TB-MIS reduce downtime, increase advance rates, and lower labor requirements. Another innovation is monolithic lining construction, where continuous or large segment linings replace traditional segmented rings. This dramatically reduces joints, one of the primary sources of leakage and misalignment. Integrated sealing systems apply membranes or coatings as part of the excavation process, ensuring airtightness without extensive post-installation work. This new era of tunnel boring transforms TB-MIS into high-precision, digitally controlled manufacturing systems, capable of delivering infrastructure that meets Hyperloop's extreme performance standards. Geological hurdles, diverse terrain, and seismic challenges. Hyperloop routes are not built in ideal geological conditions. They must traverse mountains, plains, soft soils, rock formations, fault zones, and seismic regions, all while maintaining near-perfect alignment over long distances. Geological variability is one of the greatest threats to precision tunneling. Changes in soil stiffness, rock strength, and groundwater pressure can cause uneven excavation rates, tool wear, and alignment drift. To address this, Hyperloop tunneling requires advanced geotechnical investigation far beyond conventional standards. Continuous ground probing, seismic imaging, and real-time soil characterization are integrated directly into TBM operations. Seismic regions present additional complexity. Hyperloop tunnels must withstand ground movement without losing alignment or vacuum integrity. This demands flexible joint systems, energy-absorbing linings, controlled deformation zones. Fault crossings require specially engineered tunnel sections that allow relative movement while maintaining airtight seals. Ground settlement is another critical issue. Even minor settlement can introduce vertical or horizontal deviations that compromise ultra-high-speed operation. As a result, extensive ground improvement techniques such as jet grouting, ground freezing, or deep soil mixing may be required along entire corridors. In geological terms, Hyperloop tunnels are not simply built through the ground. They are co-engineered with the ground, requiring continuous adaptation to subsurface conditions. Subsurface vs. ABOVE ground, routing strategies and engineering Trado FFS. One of the most important infrastructure decisions in Hyperloop design is whether to route the system below ground, at ground level, or above ground on pylons. Each option presents distinct engineering, economic, and operational trade-offs. Subsurface tunnels offer protection from weather, temperature fluctuations, and surface interference. They allow straighter alignments through urban areas and reduce land acquisition challenges. However, underground construction is expensive, complex, and geologically constrained. Above-ground systems, supported on pylons, reduce excavation costs and allow easier inspection and maintenance. They are particularly attractive in flat, rural regions. However, they introduce challenges related to thermal expansion due to sunlight, wind-induced vibration, visual and environmental impact. Seismic amplification at elevation ground level alignments offer a compromise, but demand extensive land acquisition and continuous protection from surface activity. From a civil engineering perspective, routing decisions influence foundation design, structural stiffness requirements, thermal movement allowances, construction methodology. Often, a hybrid approach is optimal, combining tunnels in urban or mountainous regions with elevated structures in open terrain. The routing strategy is not just a planning decision, it fundamentally shapes the engineering behavior, cost, and long-term performance of the Hyperloop system. The invisible highway, precision tracks, and levitation. Unlike roads or railways, the Hyperloop does not rely on visible tracks in the traditional sense. Instead, it operates on what can best be described as an invisible highway, a precision-engineered guideway that enables levitation, propulsion, and stability at extreme speeds. For civil engineers, this highway is not a simple support structure. It is a dynamic, interactive system that directly influences vehicle behavior. At speeds exceeding 700 miles per hour, even microscopic deviations in alignment or stiffness can generate instability, excessive vibration, or unacceptable passenger discomfort. Traditional track engineering allows for periodic maintenance and tolerances corrected over time. Hyperloop guideways must be nearly perfect from day one and capable of maintaining that precision continuously under environmental and operational loads. This demands unprecedented control over vertical and horizontal alignment, structural stiffness, and damping thermal expansion and contraction. Dynamic load transfer between pod and guideway. The guideway becomes an extension of the vehicle itself. It must respond intelligently to pod movement, environmental changes, and long-term structural behavior. Unlike conventional rail, where contact defines control, Hyperloop relies on non-contact forces, shifting engineering emphasis from wear resistance to electromagnetic compatibility and structural precision. The invisible highway represents a fundamental transformation in civil infrastructure where geometry, materials, sensors, and control systems converge to enable safe, stable, ultra-high-speed travel. Magnetic levitation systems. Inductive vs. permanent magnet. Magnetic levitation is central to Hyperloop performance, but not all maglev systems are equal. Two dominant approaches are under consideration: inductive electrodynamic levitation and permanent magnet-based levitation. Each presents distinct engineering implications for cost, scalability, and infrastructure design. Inductive systems rely on electromagnetic interaction between onboard magnets and conductive elements embedded in the guideway. As the pod moves, changing magnetic fields induce currents in the track, generating lift and stabilization forces. These systems are highly stable at high speeds and self-centering by nature. However, inductive levitation requires electrically conductive guideways, significant energy input during operation, complex cooling, and power management systems. From a civil engineering perspective, this increases infrastructure complexity and capital cost, particularly over long distances. Permanent magnet systems, in contrast, use passive magnetic arrays that generate lift without continuous power input. These systems offer improved energy efficiency and lower operational costs. However, they introduce challenges related to magnetic field uniformity, lift force variability, sensitivity to alignment errors. Permanent magnet systems place even stricter demands on guideway precision. Any geometric deviation directly affects levitation stability, transferring responsibility to structural alignment and foundation behavior. At scale, the viability of each system depends not only on vehicle design, but on infrastructure cost, maintainability, and construction tolerances. Civil engineers play a decisive role in determining which system can be realistically deployed over hundreds of kilometers. Active alignment and vibration damping. At speeds above 700 miles per hour, stability is not optional, it is existential. Even perfectly constructed infrastructure will experience ground movement, thermal expansion, material aging, and dynamic loading over time. To address this, Hyperloop systems rely on active alignment and vibration damping, transforming static infrastructure into a responsive system. Active alignment involves continuously monitoring guideway geometry and making micro-adjustments in real time. This may include adjustable support elements, actively controlled bearings, dynamic stiffness modification. Sensors embedded within the structure detect deviations as small as fractions of a millimeter, triggering corrective responses before they affect pod stability. Vibration damping is equally critical. High-speed pods generate dynamic forces that can excite resonant frequencies in the guideway. Without proper damping, vibrations can amplify, compromising structural integrity and passenger comfort. Civil engineers must design guideways with optimized stiffness-to-mass ratios, integrated damping materials, isolation systems between foundations and guideways, unlike traditional rail systems, where ballast absorbs vibration. Hyperloop guideways demand engineered damping solutions built directly into structural elements. The challenge lies in balancing rigidity and flexibility. Structures must be stiff enough to maintain alignment, yet flexible enough to absorb energy without cracking or fatigue. Active alignment transforms infrastructure into a living system, capable of adapting continuously to maintain ultra-high-speed stability. Smart tracks, sensors, real-time adjustments, and safety. Smart tracks represent the final evolution of Hyperloop guideway engineering. These tracks are not passive structures, they are intelligent systems embedded with sensors, data networks, and control mechanisms. Thousands of sensors monitor structural deformation, temperature gradients, magnetic field alignment, vibration, and acceleration, vacuum integrity. This data feeds into centralized control systems and digital twins, allowing engineers to assess infrastructure health in real time. When anomalies are detected, smart tracks enable automatic response mechanisms. These may include adjusting levitation parameters, activating damping systems, restricting pod speed, isolating affected segments. From a safety perspective, this continuous monitoring is essential. At ultra-high speeds, traditional inspection intervals are insufficient. Smart tracks allow predictive maintenance, identifying issues before they escalate into failures. For civil engineers, smart tracks demand integration of structural design, sensor placement, strategy, data reliability, and redundancy. Long-term maintainability, the infrastructure becomes both a load-bearing system and an information network. Smart tracks ensure that Hyperloop remains not only fast, but safe, resilient, and adaptable, marking a fundamental shift in how civil engineering infrastructure is conceived and managed. The future is now scaling Hyperloop. Designing a Hyperloop system is an extraordinary engineering challenge, but scaling it into a functional, global transportation network is an even greater one. At small scales, prototypes can demonstrate feasibility. At continental scales, infrastructure must prove constructability, affordability, reliability, and maintainability over decades. For civil engineers, scaling Hyperloop is not about making it faster, it's about making it repeatable. Every kilometer of tunnel, every guideway segment, and every foundation must be designed for mass production without sacrificing precision. Scaling also introduces system-level complexities, standardization across regions, compatibility with different geologies and climates, workforce training, and safety integration with existing transportation networks. Hyperloop moves from being a single mega-project to a globally replicable infrastructure model. This demands a shift from bespoke engineering solutions to modular, industrialized construction methodologies. At this stage, civil engineering becomes the bridge between visionary technology and practical reality. The future of Hyperloop depends not only on technical success, but on its ability to be built efficiently, operated safely, and justified economically. Manufacturing at scale, the industrial challenge. Scaling Hyperloop infrastructure requires an industrial effort comparable to the construction of national highway systems or global rail networks, but with far tighter tolerances and higher technical complexity. Thousands of kilometers of tunnel linings, guideway beams, pylons, seals, and magnetic components must be produced with consistent precision. Unlike traditional construction, where variability is corrected on site, Hyperloop components must arrive manufactured to specification, ready for rapid assembly. This necessitates a shift toward factory-based production. Precast ultra-high-performance concrete segments, modular steel and composite guideway elements, integrated sealing and sensor systems. Automated quality control using digital twins. Civil engineers must collaborate closely with manufacturing engineers to ensure that structural performance, durability, and constructability are embedded into the production process. Logistics become a major engineering consideration. Transporting massive yet delicate components over long distances requires careful planning, just-in-time delivery, and specialized handling. Workforce transformation is equally important. Construction shifts from labor-intensive site work to highly skilled assembly and systems integration, demanding new training models for engineers and technicians. Manufacturing at scale is not just about volume, it is about reproducibility, reliability, and life cycle performance. Hyperloop succeeds only if its infrastructure can be produced with the same consistency as modern aerospace or automotive systems. Cost vs. Benefit. Economic viability. Hyperloop infrastructure represents one of the most capital-intensive transportation projects ever proposed. Tunnels, precision guideways, vacuum systems, and magnetic levitation technology demand significant upfront investment. From an economic perspective, the critical question is not cost alone, but value over the system's lifetime. Compared to high-speed rail, Hyperloop offers dramatically reduced travel times, lower operational energy consumption due to reduced drag, potentially higher passenger throughput, minimal land acquisition for elevated or underground routes, however. Initial construction costs can exceed those of conventional rail, particularly in urban or geologically complex regions. Civil engineers play a key role in cost optimization through efficient routing strategies, modular construction methods, material selection for durability, reduced maintenance requirements. Life cycle cost analysis becomes essential. Infrastructure designed for 50 to 100 years of operation must minimize long-term maintenance, energy consumption, and downtime. Economic viability also depends on external benefits. reduced congestion, and emissions increased regional connectivity. Economic development along corridors, when evaluated holistically, Hyperloop may outperform traditional options in time savings, environmental impact, and long-term system efficiency, but only if infrastructure costs are tightly controlled through smart engineering. Beyond the blueprint, from concept to global reality, moving Hyperloop from blueprint to global reality requires more than technical success. It demands institutional, regulatory, and societal alignment. The next critical steps include full-scale pilot corridors, long-duration operational testing, development of international design standards, safety certification frameworks. Civil engineers must lead the transition from experimental projects to standardized infrastructure systems. This involves codifying best practices, defining tolerances, and establishing construction and maintenance protocols. Public acceptance is another challenge. Infrastructure must demonstrate safety, reliability, and resilience before widespread adoption. Transparent communication of engineering principles and risk mitigation strategies is essential. Integration with existing transportation networks is equally critical. Hyperloop stations, interfaces, and transfer systems must be designed as part of broader urban and regional planning efforts. Finally, global scalability requires adaptability. Hyperloop infrastructure must accommodate different climates, geologies, and regulatory environments while maintaining consistent performance. Beyond the blueprint lies the true test of engineering, turning bold ideas into infrastructure that serves society reliably for generations. Hyperloop's future will be written not in concept art, but in concrete, steel, and precision engineering. Hyperloop is more than a transportation concept. It is a stress test of modern civil engineering itself. From near-vacuum tunnels and precision-aligned guideways to smart infrastructure and industrial-scale construction, every element challenges how we design, build, and maintain the built environment. What once belonged to science fiction is now a question of engineering discipline, material innovation, and execution at scale. The future of mobility will not be defined only by speed, but by the infrastructure, intelligence, resilience, and precision that makes such speed possible. For civil engineers and engineering students, Hyperloop represents a rare opportunity to shape an entirely new class of infrastructure from first principles. If you believe engineering builds the future, you're in the right place. This is Civil Engineering Edge, where tomorrow's infrastructure is engineered today.